Hi everybody, welcome to the 4.4 notes. This is Intro to Related Rates, and some of the concepts in related rates are going to connect to what we've been learning so far in this unit. But the big idea is that in related rates problems, two variables or more than two variables are changing at the same time. And so often what's changing at the same time is time and then like something else. And so we'll look into it as we go through. But to start off with related rates, there's a concept that we have to go over. And so this these two problems right here say, suppose x and y are functions of time. Find the following derivatives with respect to t. So you might not notice this right off the bat, but in all of the problems that we've been doing so far, we have had y being a function of x. X has always been the independent variable, and then y is the dependent variable, and it always depends on x. Well, now we have two different functions. We have a function x, which is a function of t, which means time is the independent variable. And then the way that x is created is using time, right? And so x is the dependent variable. And in this function over here, we have y of t, where time is the independent variable, and then y is the dependent variable. And we've kind of had this concept before, so what we're about to do here, we've looked at before, because let's say that we're trying to figure out the derivative of something that's in implicit form, where y isn't by itself. Well, every time we did that, we would find the derivative of y and we multiply it by dy dx. And the reason we were doing that is because y was a function that was created using x. And so the x part was the inside and the y was the outside, essentially. And so we're going to look into that with some other examples here. So first, this says, find the following derivatives with respect to x. Well, the answer here can't just be 2x equals 0, because x is no longer the independent variable. X is the dependent variable and t is the dependent. And the x is the dependent variable and t is the independent variable. So what I'm going to do here is I'm going to take the derivative of both sides with respect to t this time. And this notation I'm using here, don't get too tripped up on it, but this just means take the derivative on both sides. It's kind of like you would say, like if you were solving a linear equation over here, it would be the same as doing like plus 3 on both sides. So the derivative of x squared is 2x, but because x is a function of t, I'm going to multiply it by dx dt, which was similar to what we were doing last unit when we did the derivative by dy dx. And then the derivative of 5, well, there's no variable in there, so that would be our answer. And we're not going to solve for dx dt, but that's what you would do for that problem. For the next one, we have 2y plus 4 equals 10. So the derivative of, we're going to take the derivative of both sides with respect to t. And then the derivative of 2y would be 2 times dy dt. It's not dy dx anymore because y is no longer a function of x, it's a function of t. The derivative of 4 is 0, and then the derivative of 10 is 0. So I'm going to stop there. But notice in both of these, you have, oops, sorry, I thought that was a highlighter. In both of these, you have a dx dt, dy dt. So it's the variable you're taking the derivative of with respect to t. So let's look at a couple more examples. And these ones will be a little bit nicer as we go on. So suppose x and y are both functions of time t. Let's find an equation that describes the relationship between the rate of change of x with respect to time and the rate of change of y with respect to time. So basically, now we have an equation where x and y are in them. So I will take the derivative with respect to t on both sides. And then on the left, I'll take the derivative of both terms with respect to t. So the derivative of x with respect to t is 1 times dx dt. And then the derivative of 3y with respect, of 3y with respect to t is 3 times dy dt. And then the derivative of 5 with respect to t is 0. And there's nothing else I need to do for this one. It just wants me to write an equation that describes this relationship. And so the way that you describe the relationship is it's 1 times dx dt plus 3 times dy dt equals 0. Let's do another one. So suppose x and y are both functions of time t. You have to have this sentence in order to do this. So I see the question being like, how will I know how to do this from now on? If it does not say x and y are functions of time, then you do not need to do this. Especially like if it just said like find the derivative of x squared and it doesn't have that part right there, just take it like normal. Don't overthink it ever. It'll be pretty obvious when you need to do it. So it says let's find an equation that describes the relationship between the rate of change of x with respect to time and the rate of change of y with respect to time. So take the derivative on both sides with respect to t. Feel free to try this on your own. So the derivative of x squared with respect to t is 2x times dx dt. The derivative of 16y is plus 16 times dy dt. And then the derivative of 5 is 0. And maybe you're thinking, why are we doing this dx dt part? So it's a little hard to understand, but remember that if I look over here to the side, x is a function of t. And so for this x squared right here, for this x squared guy, essentially what this is, you're doing like x of t squared. And if you look at this, this has like an inside and an outside function. And so you're basically taking the derivative of the outside, which would be like 2x, and then you would be multiplying that by the derivative of the inside, which is the derivative of x, which is dx dt. And so it's a little tricky to kind of comprehend, but that's why you're doing it this way. And then at this point, I was done with the problem. I'm just kind of trying to explain to you why it's that way. It's because if the function is made with t and you square that function, you have to use the chain rule because you have the t and you have the x. Okay, one more example, and then these ones are going to be pretty nice. So it says, let x, y, and z are functions of t. We don't have a z in here, but that's okay. Given that x equals -2, y equals 1, and dy dt equals 4 for the following equation, x squared plus y squared equals 13, find dx dt. So we want to find the derivative of x with respect to t. So to do that, if you look at this equation right here, I have no derivatives here. And so as it is, I'm not going to be able to figure this out. But what I can do is I can take the derivative of both sides with respect to t. And that will give me 2x times dx dt plus 2y times dy dt equals 0. And one thing, so this is what we need to figure out, dx dt. But the thing that's easier about these problems than what we were doing with implicit differentiation in Unit 3 is we know a lot more about values here. And so you don't have to solve for dx dt. You can just go ahead and plug in what you know about everything else. So like, for example, we know that x equals -2. We know that y equals 1. And we know that the derivative of y with respect to t is 4. And so I'm just going to plug in everything I know. So I'm going to do 2 times x is -2. I don't know what dx dt is. I'm going to do 2 times 1, because that's y, times 4 equals 0. -4 times dx dt plus 2 times 1 times 8 is, or 2 times 1 times 4 is 8. And now I'm just going to solve for dx dt as if it was just like the variable x. So like, for example, if this was over here, let's pretend that dx dt was just an x. I would subtract 8 on both sides. I get -4x equals -8. I divide -4 over here, and I get x equals 2. So if you ever get confused by this notation, just like pretend it's another variable. And so same thing, I would subtract 8 on both sides. I get -4 times dx dt. That equals -8, and then I divide -4 on both sides, and I get dx dt equals 2. And so the change of x with respect to time is t. One more example, and then we'll move on to some actual like related rates problems that you'll see more often. So example 4, the differentiable function x and y are related by the following equation, x, y equals 4. We are also given that dy dx equals 1. So also this should say that x and y are functions of time. So that's just my mistake by not writing that in the problem. So we are also given that dy dt equals 1. Find dx dt when x equals 0.5. And so we will take the derivative of this. However, we're going to take the derivative of both sides with respect to t. But something you might notice is that x times y is a product. You have two functions, function x and function y, and you're multiplying them by each other. So you have to use the product rule. So we're going to use it. So we'll start by taking, so we have two functions here, right? Function 1, function 2. So I take the derivative of x, that's 1, but because it's a function of t, it'll be times dx dt. And then I'll multiply that by just like the original second function, which is y. Then I'll do a plus sign. And then original first function times the derivative of the second function, which will be 1 times dy dt. And that equals the derivative of 4 is 0. And now I'm just going to, I know that my end goal is to find this piece of information, dx dt, but I'm just going to kind of simplify and plug in what I know. So I know that y equals 0.5 I actually don't know what x is, but x times 1, we don't need the 1 in there, but I do know that dy dt is 1, and then I have to get 0. And so the question is, this is my end goal, but I'm also missing this piece of information, which is x. However, I'm going to be able to figure it out. So I go over here and I look at the original equation. I know that x times y equals 4. And so I want to figure out what x is, and I can do that because I know what y is. Y is 0.5. So I'm going to do x times 0.5 equaling 4. If I divide 0.5 on both sides, I'm going to get x equals 8. And so I actually do have that piece of information. So I'm going to do dx dt times 0.5 plus 8 times 1 equals 0. And now I can just solve for this dx dt, and I'm just thinking about it as if it was just a variable. So 8 times 1 is 8, so I'm just going to go ahead and subtract 8 on both sides. I'll get dx dt times 0.5 equaling negative 8. I'll divide by 0.5 on both sides, and I'll get the change of x with respect to time is negative 16. So that is our first set of problems. Now we're going to go into some problems that kind of connect why have we been learning implicit differentiation? Why did we do all these funky problems? And it's because this can connect to real world skills, but we have to learn the skill before we can kind of use it. So related rates, I'm going to read this paragraph to you, but feel free to read it over, annotate it yourself. One thing that distinguishes calculus from algebra is its ability to deal with variables that change over time. I'm going to highlight that. We do this by differentiating the function implicitly with respect to time. These problems, we have one rate of change and seek to find another, are called related rates. I'll highlight that. So the things that we have to do to solve these problems. Number one, we need to understand the problem. So you will identify your variables whose rate of change you know and whose rate of change you seek to find, which is kind of what we were just doing. Like if you guys notice in all those problems, I was highlighting what we needed to find. You'll develop a mathematical model of this problem. Draw a picture and label what you're given. So this concept right here, we'll draw a picture. That's just going to help us understand the problem a little bit deeper. Write an equation relating the variables whose rate of change you would like to know. This can often be geometric, like the Pythagorean theorem, or area or volume. Differentiate both sides of the equation implicitly. And then we'll do that with respect to time. So dx dt, dy dt, dz dt. Substitute values for any quantities that depend on time, and then interpret the solution. So kind of like what we've been doing, we have to explain what our answers mean in the context of the situation. Context. So you can highlight what you wanted and highlight. You don't have to highlight what I did. So let's look at a problem. Example 5. The sides of a square are increasing at a rate of 0 centimeters per second. How fast is the area enclosed by the square increasing when the area is 100 centimeters squared? So imagine. So the first step, I'm going to scroll back up, is to understand the problem. So what are we trying to figure out? It says, how fast is the area enclosed by the square decreasing when the area is 100 centimeters squared? So what we're trying to figure out is how fast is the area increasing, and specifically the area of the square. And so what we're trying to figure out over here is we're trying to figure out the change in the area with respect to time. And so what we're trying to figure out is dA dt, where A stands for the area. So that's what our end goal is. Our end goal is to figure that out. And so before I kind of write out like equations and stuff, let me just picture what's going on. Basically, we have this square, and the square is increasing. All of the sides, specifically the sides of the square, are increasing. And obviously, if the sides of the square increase, the area of the square is going to increase too, right? If I put another larger square, like that square right there has larger sides, it's increasing. And so that's what's kind of happening here. And so there's some pieces of information we don't know, right? We don't know the change in area over the change in time. But let's figure out, question number 3 says, write an equation relating the variable. So I guess we can do that part next. We have a couple variables here. We have sides of a square, and then we have area of a square. And so to think of how do sides of a square and area of a square relate, we just need the area formula. And if it's a square, the area of a square is s squared equals a. So basically it's side times side equals a. And so to do that, let's think. The sides of the square are increasing. So it says increasing at a rate of, which means we know the derivative. And so we know that as time is passing, ds dt, the change in the side lengths over time, is 10 centimeters per second. and it's increasing, so it's positive. So it tells us that piece of information. And then it says how fast is the area enclosed by the square increasing, so that's what we don't know. But then it says when the area is 100 centimeters squared. So we know that the area is 100 centimeters squared. And then also, we don't know if we necessarily need this information yet, but if the area of the square is 100, then we can go ahead and figure out, I'll just do it over here to the side. If the area is 100, then that means if I take the square root of both sides, that the side length is 10. So we also know that the side length is 10. So we have done step 3 now. Step 3 was to write an equation, we need to write an equation, which we did. And then we wrote the variables that we would like to know of the rate of change. So now our next step is to take the derivative of both sides with respect to t. So I'm going to take the derivative of both sides with respect to t. And then the derivative of s squared is going to be 2s times ds dt. And then the derivative of a is going to be 1 times dA dt. And our goal is to figure out this piece of information. And so I already kind of did all the work out on the side because I know what all these things are, right? We figured out that the side length was 10. And we figured out that the change in the side length over time is 10. And then 1 times dA dt is just dA dt. 2 times 10 times 10 is 200 dA dt. And so the last step we need to do is we substituted the values there. We need to interpret the solution. And so because this is the change in area over time, that's going to be the area is increasing at a rate of 200, it was centimeters, centimeters squared per second, and it's centimeters squared because area is squared, and that is our answer. So let's look at one more, maybe 2 more. We'll see the timing. So a circle's radius is decreasing at a rate of 2 centimeters per second. At a certain point, it has a radius of 10 centimeters. At that point, what rate is the area growing at? So let's draw our model first. We have a circle, and it has a radius. And so remember, this is the radius. And our radius is actually shrinking. It's starting to get smaller and smaller, okay? So imagine it getting smaller, and if the radius is smaller, then that means that our circle is getting smaller. So our circle is going to be moving, and it's going to be getting a little smaller. So that's what's going on. At what point, so our final thing is what point, at that point, what rate is the area growing at? So what we're concerned about, again, as like the last one, is we're concerned about what the area is growing at. What rate is it growing at? So again, we're concerned about dA dt for this problem. And so reading back over, it says the circle's radius is decreasing, and then it also talks about the area. And so the only formula that we have, or the only formula we need to connect those two variables, a radius and the area, is the area formula of a circle, which is pi r squared. That equals the area. And so let's look at what else I have. So dA dt is what I need, right? And this also says a circle's radius is decreasing. So we know that dr dt, the change in the radius over time, is 2 centimeters per second, but it's actually going to be -2 because it says it's decreasing. And it says at a certain point, it has a radius of 10 centimeters. So we know that r is 10. And then we don't know the area, but we're going to pause and we're going to take the derivative to see, do we actually need the area? Last time it was like really easy to figure out what the side length was, but it's not as easy to figure out what the area is here. So I'm going to go here now, and I'm going to, so the steps I'm doing on the left are just setting up my problem so that when I go and do my problem, everything's a little bit easier. And if I need more things, I can add them later. But I'm going to take the area, or the derivative of both sides. Pi r squared, the derivative of that is pi times 2r, and then because it is r is a function of time, I'll multiply that by dr dt, and the derivative of a is 1, and because a is a function of time, I'll do it times dA dt. And now I'll plug in what I know. So I'm just going to rewrite it as 2 pi, and then r, we did the work over here, and we got that was 10, and then the change in the radius over the change in time was -2, and then we just have dA dt over here. 2 times 10 times -2 is -20, and I'm just going to leave it as -20 pi because you normally don't simplify when you're using pi. And so the area is changing at a rate of -20 pi centimeters squared per second. And you also could have put the radius is decreasing at a rate of positive 20 centimeters per squared per second. But because I didn't say decreasing, I kept that word negative. Also, did I do some math wrong? I think it should be negative 40. My bad, because 2 times negative 2 is 4. So negative 40.